All right, problem 6 says a function f has derivatives at all orders for all real numbers x. A portion of the graph of f is shown above, along with the line tangent to the graph of f at x equals 0. Selected derivatives of f at x equals 0 are given in the table above. For part A, they want us to write the third degree Taylor polynomial for f about x equals 0. So for this, the formula that you are going to reach for is Formula 101, the nth degree Taylor polynomial centered at x equals c. It's just that we're going to let all the c's be zeros. So the function would be approximately equal to, in this case, f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial, and so on with that pattern. So let's get started with that. So part A, f of x would be approximately f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed. And then they said third degree, so I guess I can stop there. There we go. Okay, so now let's just fill in the values. So we can use the graph to get f of 0, since they said this is f. And so f of 0 looks like would be 3. We can also use the graph to get f prime of 0, since they gave you the tangent line here. So f prime of 0 would be, looks like down 2 to the right 1, so it would be negative 2. And then the table over here is how we'll get the other derivatives. So according to the table, when your number, n means the number of derivatives, you can tell because it's in parentheses. So your second derivative at 0 is 3. And your third derivative at 0 is negative 23 over 2. Like so. And they gave you one more row, which I think we end up using later in the problem, but for now we wouldn't need it. So let me just kind of simplify what we've got here. We've got 3 minus 2x plus, I'll just call that 3 halves, x squared minus 23 over 12 with the 2 and the 3 factorial. There we go. I think a different version of notation could be p sub 3 of x is equal to. I prefer this because it reminds me that this would be just an approximation for the function values that are close to 0. So, okay, I think that's it for part A. For part B, it says write the first 3 non-zero terms of the Maclaurin series for e to the x. Let's do that. Then they want the second degree Taylor polynomial for e to the x times f of x about x equals 0. So, all right, let's get the Maclaurin series for e to the x. I hope that you do have this one memorized. This, my friends, would be 104. As helpful would be 102 and 103. So you want to go into the test knowing those 3. So e to the x is equal to 1 plus x squared over 2, or 2 factorial. I guess I'm going to write that as 1/2 x squared. Plus 1 over 3 factorial times x cubed. First 3 non-zero terms. 1, 2, 3. I guess that's just that. And I would say e to the x is approximately then. Okay? Okay, so that's that. Write the secondary Taylor polynomial for e to the x times f of x. Okay, so e to the x times f of x just means, as far as polynomials go, we're going to take this polynomial, 1 plus x plus 1/2 x squared, which we could always build more in, right? 1 over 3 factorial x cubed. We could always put more in if we want. I don't think we really need that, but you could put that there. And then f of x is this thing, 3 minus 2x plus 3 halves x squared minus 23 over 12 x cubed, etc. you need the plus dot 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 if you're going to say exactly equal to. And then as far as what to do, we're just going to multiply them together, and then we only have to get up to the second degree. And so you just multiply it out until you know you're right up to the second degree. So let's get started. So we're going to distribute 1 in. So we'd have 3 plus, all right, distribute it in, plus, I guess I should say minus 2x. Plus 3 halves x squared. And then there's no need to keep distributing it past this term because I just need my answer to be correct up to the second degree. So I would just say like, and there's more to it, right? But then you multiply the x in and you'd add it to this stuff. So I'm going to multiply the x in, so I'd have 3x, and I'm going to line it up by like terms. So 3x minus 2x squared plus 3 halves x cubed, which I guess I didn't need to write that, right? Because I only need to be correct up to the second power, so I'll just say doop, doop, doop. Now let's multiply 1/2 x squared in, so you'd have 1/2 x squared times 3, so 3 halves x squared. 1/2 x squared times negative 2x would be cubed, and so we didn't really need the rest of that either. And then you just add it up. So e to the x times f of x would be approximately 3, negative 2x plus 3x is x. Looks like 3x squared take away 2, so oops, I guess not. I'm just going to say approximately and then just put the terms. There you go. So just polynomial multiplication, and that's it for that. Okay, so that's part B. Part C, let h be the function defined by h of x equaling the integral from 0 to x of f dt. Use the Taylor polynomial found in part A to find an approximation for h of 1. So, let's see. In part A, we have an approximation for f of x. So let's think about for part C. We said h of x is defined as the integral from 0 to x of f of t dt. Okay, so let's use the fundamental theorem of calculus on this. So this would be the antiderivative of f with x plugged in, take away the antiderivative of f with 0 plugged in. And then if I want to know what h of 1 is, that would just mean replace all the x's with 1s. So that means we just take our answer from part A, which was f of x, and do antiderivative term by term. So I'll just make a note off to the side. Okay, so we're just going to look up here. So antiderivative of 3 would be 3x. Antiderivative negative 2x, negative x squared. Antiderivative 3 halves x squared would be 1/2 x cubed. Antiderivative of 23 over 12 x cubed would be 23 over 48 x to the 4th, I think. Okay, so that's the antiderivative. Oh, and then I guess there's more to it. Or you could say approximately. So the antiderivative evaluated at 1 would be approximately 3 minus 1 plus 1/2 minus 23 over 48. And then you could simplify it. So 2.5 take away, so 2.5 is like 2 and 24 28ths, or 24 48ths. Take away 23 48ths. So f of 1 is approximately 2 and 1/48ths. And then what would big F of 0 be? Well, that would just be plugging zeros in, and since everything has an x in it, that would definitely be 0. Okay, so it looks like h of 1 would be approximately 2 and 1/48. Okay, let's see how that's, is that all they asked us for? That is all they asked us for. Okay. Okay, part D, this should be a good time. Okay, part D. It is known that the Maclaurin series for h converges to h of x for all real numbers x. It is also known that the individual terms of the series for h of 1 alternate in sign and decrease in absolute value to 0. Use the alternating series error bound to show that the approximation found in part C differs from h of 1 by at most 0.45. Okay, so the language that they're using here leads me to think about the alternating series remainder theorem. And just to make sure, double check. So this is something that would be a good card to play at this time. For any convergent alternating series, which we know it is because they said that it alternates in sign and decreases in value to 0, the difference between the infinite sum and any nth partial sum is less than the absolute value of the first neglected term. So this is what we're going to reach for. So first thing you want to do is explain that since h of 1 is a convergent alternating series, the difference between actual h of 1, and 2 and 1/48 is less than the magnitude of first neglected term. You want to have that little piece memorized so that you could use it. And now let's be specific as to what we're saying. We're saying if you subtract the real h of 1 and our little approximation that we got and take the absolute value, so this would be the error, the difference between the two, then you're guaranteed to have that be less than the absolute value of the first neglected term. So now, with the second color, I'm going to go through and show you how to get that first neglected term. So it would start by coming up here and figuring out what was the first neglected term for f of x. And so go back to how we got these. So the first neglected term would have been the fourth derivative at 0 over 4 factorial times x to the fourth. And that's where this line could come in handy. So the fourth derivative at 0 of the function is 54. So this would have been 54 over 4 factorial times x to the fourth, like that, which you could simplify down with 4 factorial being 432 and 54. You could cancel it down to be 9/4, like so. So if that would have been the first neglected term, like so, did I do that right? I think so. Then what would the first neglected term have been of its antiderivative? So just do antiderivative, power rule that thing, and you would have gotten 9 over 20 x to the fifth. So this would have been your first neglected term. And then when you plugged 1 into it, your first neglected term would have been 9/20ths. Hopefully that makes sense. So that's what would go here. I guess I should put in blue, because I was just putting the stuff in red to kind of show like how I figured it out, but it's not really part of my, I don't want it to really change my work. And then you could, so you've got, so 9 over 20 is the same as 45 over 100, which is equal to 0.45. There we go. That's that.